In this video, we complete our discussion of concepts for Chapter 10. And here we look at molecular shape and molecular polarity. In our last video, we left off looking at the shapes around the carbon atoms in ethane, which are both tetrahedral, and around the carbon atoms in ethanol, which again are both tetrahedral, though their bond angles are slightly different. And around the oxygen atom in ethanol, which is a tetrahedral electron group arrangement, but with two lone pairs, is a bent structure. And the carbon-oxygen-hydrogen bond angle is less than 109.5 based on a simple tetrahedral electron group arrangement because the lone pairs occupy more space. Molecular shape is tied very closely to molecular polarity. Overall, the molecular polarity depends both on the shape of the molecule and the individual bond polarities. And the bond polarities, as we talked about in the last chapter, are derived from differences in electronegativities. The polarity of a molecule is measured by what is called its dipole moment, which is given the Greek letter mu. That's the dipole moment, and is typically in the units of debye. That is D. We will not use these units, and we won't do calculations on this. This is just a unit that you will see, and as you look up dipole moments, you may see those. This is something that you would have a little bit of familiarity with. A molecule is polar, then, if it contains at least one polar bond, that is, with an electronegativity difference between the two atoms, and the individual bond dipoles that add up if there are multiple bonds, and if they do not cancel with one another. Let's look at examples in just a moment. We'll start off with a simple diatomic. That's hydrogen fluoride. So we've looked at hydrogen fluoride. We spent a fair amount of time on that in Chapter 9 when we were looking at covalent bonds and polar covalent bonds. We know the fluorine side of this molecule is negative. The electrons in the bonding pair tend to be drawn over towards the fluorine side, such that the hydrogen is electron deficient and appears to have a partially positive charge on it. And if you take a vapor of hydrogen fluoride molecules and you put it between two parallel metal plates, if there's no voltage applied to those plates, the molecules will be randomly oriented. But if we apply a high voltage to this, the molecules then begin to align in the electric field. The molecules become what we call oriented. The fluorine ends will point towards the positive plate, and the hydrogen ends will point towards the negative plate because of the dipole moment on the molecule. Now we go to more complicated molecules. And let's take as our first example, carbon dioxide. Carbon dioxide, of course, has two atoms, carbon and oxygen, with an electronegativity difference of 1.0, oxygen being 3.5, carbon being 2.5. And so we would expect the carbon-oxygen bonds to be indeed polar, which they are. And in general, the carbon side is positive and the oxygen side is negative. Well, there is one exception to that, and it's carbon monoxide, which shows some unusual behavior. And if you're interested in that, your book talks about it, and we can discuss it some in your discussion section. If we draw the Lewis dot structure for carbon dioxide, the central carbon atom has two double bonds. One pair of double bonds goes to one oxygen, and the other pair of double bonds goes to the other oxygen. And of course, each of these carbon-oxygen bonds has a dipole, but they're pointed in opposite directions. So you can think of this as a tug of war, but each of the oxygen atoms are identical. So those identical twins pull on the central carbon atom, and that carbon atom doesn't move in either direction. So what happens then is the carbon region is slightly positive, and the oxygens are slightly negative, but as we look at the molecule overall, it has no net dipole moment. H2O is another example of three atoms. In this case, the hydrogen atom is less electronegative at 2.1, and the oxygen is more electronegative at 3.5. So we expect each oxygen-hydrogen bond to be polar, and indeed they are. The oxygen end is negative. If we look at water, the Lewis dot structure shows us, as shown here, we have two lone pairs and two bonding pairs around the central oxygen atom. Now, if we apply VSEPR to this, this is a tetrahedral electron group arrangement with two lone pairs. The molecular structure is bent. So, indeed, water has a V-shaped geometry. Now, in this case, the oxygen-hydrogen bonds, each one of them has the hydrogen end positive pointing towards the oxygen. So the oxygen end of this molecule is slightly negative. This is not because of the lone pairs. It is because of the bonding pair between the hydrogen and the oxygen. The hydrogen becoming slightly positive because it has lower electronegativity and its electrons are bled more over towards the oxygen atom. And in this case, since both hydrogen atoms are downward, they're not in a straight line, their bond polarities don't cancel. This molecule has an overall molecular polarity, with the oxygen end being positive or negative and the hydrogen end being positive. We can have molecules that have the same shape but don't have the same polarity. And a simple example of this is comparing carbon tetrachloride. The carbon has 4 bonds, as it always has, and the central carbon having 4 bonds around it, and the chlorines being more electronegative, they all draw away more electron density. The carbon becomes slightly positive in this structure. But since all 4 of them are at 109.5 degrees relative to one another, all of their dipoles cancel. Carbon tetrachloride is a non-polar molecule. In contrast, the molecule here, chloroform, carbon with 1 hydrogen and 3 chlorines, does have a net dipole moment. The carbon and the hydrogen, of course, has carbon slight polarization towards the carbon. But then the carbon and the chlorines all have a significant polarization out to the chlorines. And so the chlorine end of the molecule is negatively charged. The hydrogen end is positively charged. And this molecule indeed has a dipole moment of 1.01 debye. Another example is that of dichloroethene. This is this molecule here. You would not need to name this molecule. You'll name that when you get to organic chemistry. There are 2 different versions of C2H2Cl2 shown on the left and right panels here. You can see that both have a carbon-carbon double bond, and both of them have 1 hydrogen and 1 chlorine attached. But the chlorines can be on the same side or on opposite sides. If the chlorines are on the same side, this molecule is flat, and the chlorine half of this flat molecule is negative, and the hydrogen end is positive. That molecule has a dipole moment. The trans molecule does not have a dipole moment. The carbon and chlorines cancel one another, as do the carbon and hydrogen. Now, one has a dipole moment, that is the cis, and one does not have a dipole moment, that is the trans. The boiling point of the cis isomer turns out to be 13 degrees higher than that of the trans isomer, even though they have the same molecular formula and they have identical bonding from a simple perspective. 2 carbon chlorine bonds, 2 carbon hydrogen bonds, and 1 carbon carbon double bond. As we said before, we look at the electronegativity differences for each individual bond to tell us the bond polarity, and we take these in aggregate to determine the overall molecular polarity. The molecular polarity tells us about intermolecular forces, which, as we'll see in Chapter 12, will tell us about solubilities, reactivities, and overall physical properties of the system.